Okay, hey everyone, welcome to part two of uh, our lectures on this time solving linear systems. So last time we talked about Gauss-Jordan elimination, and sort of with that was row echelon form of a matrix. And so we just have to finish the conversation. So this will be a shorter video, and this time, what we talk about is something called Gauss-Jordan elimination, because two mathematicians are get the credit for this method. I've got a quote here. This one's strictly better. It's like simplifying a fraction all the way down instead of part way. This was by a friend of mine who's a former linear algebra student. Um, Now, there's something about Gauss-Jordan elimination which feels like it's more complete than just Gaussian elimination, where we reduce a matrix to row echelon form. Well, we'll start off this time with a different form of a matrix called reduced row echelon form. So a matrix is in reduced row echelon form if number one, well, has to be in row echelon form, of course. Number two, okay, so we have leading, remember row echelon form was the descending staircase, and it wasn't necessarily a perfect right triangle, right? You could have a couple of, it's more like a descending triangle. Anyway, descending staircase. So we maintain that descending staircase pattern, but now we just ask that the leading entry, every time you have a leading entry, it must be the number one. So if in your row echelon form of your matrix, you had a leading entry which was not a one, you're going to have to scale down that row so that it is a one. Okay. And then we take it a step further and say that if you have a leading one, oh, by the way, we call the leading entries that have to be ones, we call those leading ones in reduced row echelon form. Okay. And then our third point is that if you have a column that contains a leading one, that column has to have zeros everywhere else, above and below the one. Okay, so let me show you just a nice big matrix that's in reduced row echelon form. So row echelon form, still we have our leading ones. Every single one of them has to be to the left of all of the leading ones below it. If we have a row of all zeros, in this case we do, that has to occur at the bottom. And now, if you look, these columns, first of all, the fact that the leading entries are all ones is part two of our definition. But also, if you look at the columns corresponding to the leading ones, notice the only non-zero entry in each of those columns is precisely the one, the leading one. Okay, so that's what reduced row echelon form looks like. The reason for such a crazy, way of crazy definition for the form of a matrix is because with this form, it's going to make back substitution not just easy, but more like instantaneous. It'll be so straightforward to do back substitution that it doesn't really even get a step anymore. Okay. Here's a fact that beautiful word, unique. Here's a fact that is not obvious. So remember we remember that for row echelon form of a matrix, you could have several different forms of several different equivalent row equivalent forms of the same matrix, which are all in row echelon form, but that are different from one another. And for that reason, we said that row echelon form of a matrix was not unique. But reduced row echelon form for a matrix is surprisingly, like, it's not obvious, but it is unique. There's only one way to write any given matrix in a reduced row echelon form. It's a very, very handy property. Also, beautiful word, unique. You might describe this word as unique. Anyway, okay, great. My wife did that. Okay, so Gauss-Jordan elimination. So now let's see how this is different from regular Gaussian elimination. For those of you who just finished watching the other video, you're going to recognize this as a copy-paste. There is precisely one word that is different in Gauss-Jordan elimination versus Gaussian elimination. It's this word reduced. Okay. Yeah, step 3 is solve the resulting linear system using back substitution. But like the resulting linear system, there's no back, like this back substitution is misleading. Because of the shape of reduced row echelon form, we don't just do back substitution to solve the resulting linear system. We just read off the final answer. So I'm going to show you what that looks like. And we'll bring up an example that we used last time. So this linear system has the augmented matrix 1, minus 1, minus 1, 2, augment 1, and then 2, minus 2, minus 1, 3, 3. And then minus 1, 1, minus 1, 0, minus 3. Now, what we did before was go to reduced echelon form. I'm just going to skip right there. The reduced echelon form, the row echelon form for this matrix was 1, minus 1, minus 1, 2, 1, 0, 0, 1, minus 1, 1, and then 0, 0, 0, 0, 0. Okay. This was the reduced echelon form for this matrix. To get this thing, this is the row echelon form for this matrix. To get it into reduced row echelon form, we have one more step to do. Notice the leading entries are already 1s, and it's in row echelon form. So all that's left is to make sure that the columns have any column that has a leading 1 in it has only zeros in that column. Well, amazingly, the first column already has that property. It's got a 1 and only other zeros. So the only thing that has to change is that this number needs to become a 0. And we can do that with one step. Just add row 2 to row 1. So row 1 plus row 2 gives us, well, the first two numbers don't change because you're adding 0. Then negative 1 plus 1 is 0. 2 plus negative 1 is 1. And 1 plus 1 is 2. The second row hasn't changed. And the last row is still just a row of all zeros. This is now in reduced row echelon form, because look, this column now has the only non-zero entry is that leading 1. So this is reduced row echelon form. Okay. Let's convert this back into a linear system. It reads W minus X plus Z equals 2, and Y minus Z equals 2. Now, Z is a free variable, and Y is a free X is a free variable, excuse me. X and Z are free variables. And in order to solve for W and Y, we just isolate those variables. Take the Z's and the X's and everything else to the other side of the equation. So in other words, W equals 2 plus X minus Z. X is a free variable, it's just X. Y is 2 plus Z. And Z is also a free variable. We're done. That's all there is to it. Granted, I skipped a lot of the work here because we did it last time. Right, but notice if we had just done one more step, we would have bypassed all of the back substitution. That's the utility of Gauss-Jordan elimination. Sort of eliminating all the, like, Gaussian elimination is eliminating enough so that you can solve the linear system. Gauss-Jordan elimination is eliminating all the way down to the end, so that all you have to do is convert back into a linear system and read off your final answers. By the way, I want to mention how we would go about reporting the final answer for this one. So last time we just said, like, oh, write it as a linear combination of some vectors. We'll still do that, but I want to write it. I want to write the corresponding solution set as in parametric form, we'll say. So define parameters. So this is just final answer. Define parameters s equals x and t equals z. The reason I would want to do this is because parameters are like variables that change, but that will keep us within the solution set. And so, in other words, so what we can do as our final answer is we can write w, x, y, z. A solution to this system of linear equations can be written as just the same as what we had before. So the constant vector 2, 0, 2, 0 plus we're going to have a vector containing s's. So anything that has an x in it. S, 0, 0. And a vector containing t's. That's anything that has a z in it. So negative 1, 0, 1, 1. Sorry, t's everywhere. Negative t, 0, t, t. Okay? You can also write it like this. 2 plus s minus t. You'll recognize that as a linear combination of these variables. 0 plus s minus 0, or plus 0. Okay, 2 plus t and t. Either one is acceptable. Both are a parametric description for the solution set. Okay. Okay, great. So let's do a geometry type problem rather than keep everything in the realm of algebra, right? So we're given the equation of two planes. Now then we're asked for their intersection line. So we first have to ask, like, do these lines intersect? And the answer is yes, because okay. So these planes do intersect. For a reason, we'll cover it. I'll give you a description. Their normal vectors are not parallel. Two planes will fail to intersect along a line precisely when their normal vectors are parallel. This is equivalent to the statement about slope the slopes of two lines. So like two lines will fail to intersect precisely when they have the same slope. But you could also say that the normal vector to a line, to two lines which fail to intersect, those two normal vectors have to be parallel. Okay. Now, what is normal? Normal is perpendicular. If you remember when we were talking about the dot product, we talked about this notion of orthogonality. That's two vectors are orthogonal to one another if they're at right angles to one another. And that happened precisely when the dot product of those two vectors was 0. Well, suppose I had some plane and I want to take a vector, draw a vector that is normal or that is orthogonal to every vector inside that plane. Okay, what would I have to do? It would have to be standing like a tree trunk coming out of the ground. Yeah, it has to be sprouting out of that plane. Now, because vectors in standard position and everything else like that, we can move the vector to any point on the plane. The only thing that matters is its direction and magnitude. Usually what we do to denote the normal vector is we do there's one vector which is normal to every other vector, and it's precisely the one obtained by reading off the coefficients in the equation defining that plane. So the normal vector to a plane ax plus by plus cz equals d is the vector ABC, usually denoted with an n. N equals ABC. Very nice. And what does it mean for two vectors to be parallel? Well, since we're looking at I'll show you in the two-dimensional case. Take a vector, put it in standard position so that its tail is at the origin. Take another vector which is parallel to it, put it in standard position so that its tail is at the origin. What does it mean for two vectors to be parallel? It means that if they're in standard position, then one must be a scalar multiple of the other one. And notice this vector is this normal vector ABC is assumed to be in standard position. So when we write down just the coefficients of this plane, move the vector to the origin, and we automatically have it in standard position. So what we ask is 1, 2, minus 1, and 2, 3, 1. Okay, these guys are definitely, one is not a scalar multiple of the other one. Clearly, right? What would you have to do to this one in order to get to this one? You have to multiply it by 2. Okay, but that would get the first entries to line up, but then the second entry fails, right? So these guys are not parallel, which means that the planes don't stand a chance at being parallel, which means they must intersect along a line. Great. So we okay, but the problem we didn't need to know any of that in order to solve this problem, because it says find the line of intersection for these planes. Right. We didn't need to know that, but it is a really cool geometry thing, and it helps to set the stage a little bit. So okay, so what do we actually do? We have to write down a system of linear equations, and here it's just a system of two linear equations, specifically the equations of two planes. It's x plus 2y minus z equals 3, and 2x plus 3y plus z equals 1. Okay, and now we're going to use Gauss-Jordan elimination to solve this. So first we have to convert this into an augmented matrix. 1, 2, minus 1, 3, 2, 3, 1, 1. And then we have to go and row reduce. Now notice there's already a 1 in the top left corner. And so we're going to use that as our leading one and pivot around it, which means we should subtract 2 copies of row 1 from row 2. So in other words, row 2 minus 2 row 1. Okay. The first row doesn't change. 1, 2, minus 1, 3. The second row, when we take away 2, 2 minus 2 is 0, of course. 3 minus 4 is negative 1. 1 plus 2 is 3. And then 1 minus 6 is negative 5. Okay, great. We can now, first thing we have to do now, remember, so this, by the way, this is in row echelon form, but we want it in reduced row echelon form, just to illustrate the point, which means that this bottom row needs to have a 1 as the leading entry. It's a negative 1 at the moment, so we have to negate the second row. So minus R2. First row stays the same. 1, 2, minus 1, 3. Second row becomes 0, 1, minus 3, 5. Okay, and now the last step is to, we have to get this entire column to be a 1 and zeros everywhere else. So we have to take negative 2 copies of the bottom row and add it to the top row. So row 1 minus 2 row 2. The bottom row will stay the same, 0, 1, minus 3, 5. And the top row, the 1 will stay the same, 2 minus 2 is 0. Negative 1 plus 6 is 5. And negative 10 plus 3 is negative 7. Okay. Now we can convert this back into a linear system. The linear system is x minus 5z equals negative 7, and y minus 3z. Oh, sorry, that first one should be x plus 5z, right? Positive 5. The second one should be y minus 3z equals 5. Good. Notice z is a free variable. So we let s, or t, I'll do t, let t equal z. In that case, solutions will be of the form x, y, z equals z is just t, x, I guess maybe I should start with x. Okay, x is really negative 7 minus 5z, but z is t. So this is just negative 7 minus 5t. Y is 5 plus 3z, so we should write this as 5 plus 3t, and z is just t. Okay, and if we're writing it in the vector form of an equation, it'll look exactly the same, but separated as 2 vectors. One vector as like the constant vector, and then t times the linear vector. Anyway, it'll be negative 7, 5, 0 plus t times negative 5, 3, 1. Again, either form is acceptable. Okay, great. So the last thing we have is a definition for homogeneous systems. This is the first time that we're going to see homogeneous systems, but it is not the last time. In fact, linear algebra behaves really, really nicely when we're dealing with a homogeneous system. What does that mean? It's just an extra adjective that we put in front of a system of linear equations. We say that such a system is homogeneous if the constant term is equal to 0. And I've written down some examples, but notice, right? Same thing as normal. You just have a linear system, as always, but all of the constants are 0. Okay, if we were to write this as an augmented matrix, notice we're writing it as like A augmented with the 0 vector. Interesting. Something that's very interesting is that this thing always has at least one solution. Before I just say it, I'll just say it. It's the 0 vector, right? If you plug in zeros for all of the x, y, z, w, all the variables, plug in 0 for all of them, I promise you'll get a solution to this system of equations, right? Because what happens when you add 0 to itself a bunch of times? You get equal to 0. But that's the constant in every single equation, 0, right? So the 0 vector is always a solution to every equation in a homogeneous linear system. You could have other solutions, and we'll talk about that in a moment. So like I said, the unique solution is the 0 vector. Oh, sorry. If there is a unique solution, right? So in particular, these systems are always consistent. But so unfortunately, we don't know if there's going to be a unique solution or infinitely many solutions. But if there is a unique solution, that solution will be the 0 vector. And if there are and if it's not the unique solution, then there's at least 2. But remember, if there's at least 2 solutions to a system of linear equations, then there are infinitely many. Right? We talked about that in section 2.1. Okay, so we do have a theorem to end on. This is a consequence of the rank theorem. So it says if A augmented with 0 is a homogeneous system of m linear equations with n variables, where m is less than n, then the system will have infinitely many solutions. So what is this saying? We have fewer linear equations than we have variables. Okay, when that happens, we have infinitely many solutions. So first of all, the first thing that we should mention is that the system is consistent. Okay. The second thing that we should mention is that notice the rank. So the rank of A. Remember, that was the number of non-zero rows. Okay? I can tell you that's going to be at least, at most m. Why? Because every linear equation defines a row, and after doing reduced row echelon form or whatever, you might have a row of all zeros, and a row of all zeros will not have a leading 1. And then beyond that, you have a leading 1 in every single row, which means that you have at most m leading 1s. But you'll have less if you have rows of zeros, right? So the rank is no bigger than m. But now, the number of free variables Oh, this is the rank theorem tells us that the number of free variables is precisely n minus the rank, right? This is just the statement of the rank theorem. But if I'm going to subtract the rank of A, that's subtracting a number which is smaller than or equal to m. So this number that I've constructed is greater than or equal to n minus m, right? If I subtract a number which is smaller than m, I'll end up with a number which is bigger than if I had subtracted just m. Or if they're all equal, they're all equal. But by hypothesis, like by the assumption in our theorem, there were fewer rows, there were fewer linear equations than there were variables, which means that n minus m is a positive number. Strictly positive. Now, hang on a second. That means I'm guaranteed to have a free variable. And if I have a free variable, so I'll just put, okay, yeah. Since I have a free variable, guaranteed free variable, then I must have infinitely many solutions. There's your little tombstone. End of proof. QED. So that's actually all for this video. It's a short video. That's because I really misjudged where to cut the previous video. But okay, we'll get this one out of the way, and then all that's left for week 2 will be the video for section 2.3, and that will be a long video. I apologize in advance. But it's a great topic, and I will see you then.